In this section, we're going to look at the fundamental theorem of calculus. This is going to allow us to interpret the definite integral as total change from rate of change. So we are looking at the integral as the antiderivative. We're going to use the notation in the units to interpret the definite integral. And of course, we're going to learn to apply the fundamental theorem of calculus. And the point of this section is to relate these ideas we've talked about in the last few sections to the derivative and to this thing we're going to call the antiderivative. So let's first start by looking at an example we've looked at before in this chapter. This table below shows the velocity of a bike moving along a straight road at different times, in this case, half-second intervals. We want to ask the question, how far has the bike gone in 4 minutes? So we learned that this is going to be the area under the curve. So we can say distance traveled is area under the curve. And we can estimate that using rectangles, in this case at half-second intervals, because that's the units that were given for this function, or the points were given for this function. This is going to be a left Riemann sum that we use to estimate the integral. But in the last section, we learned that the actual area is going to be equal to the integral from 0 to 4 of the function v of t dt. That this definite integral represents the distance traveled. So using that, we know distance traveled is the area under the curve is going to be the integral from a to b of the velocity v of t dt. And we kind of know what some of these things mean. We know that v of t is our function that we're looking at. We know dt is a infinitely small change in t. We know a and b are the bounds. So that's going to be from t equals a to t equals b. And then the integral tells us to add up a bunch of different rectangles. So apart from that, we can also think about distance in a different way. We know that the distance traveled total is going to be the change in the distance, p of 4 minus p of 0. So here, p of t is going to be the position function. So if we know that at t equals 0, let's say p is 0, that is p of 0 is 0. And then at p of 4, at t equals 4, we have, say, like 20, then we know total, we've gone 20 units. Now, in that time, we may have gone back and forth at different times, and we may not have gone the same speed the whole time, but we know that that's going to be the distance traveled. So in general, you can take the last distance value minus the first distance value, and that's going to give you the total change in the distance. So we get this formula in terms of velocity and position, that the area under the curve, the distance traveled, is just going to be the change in the distance function. Now this is actually a very simple idea, but why we haven't talked about it before is because we were given information just about the derivative, and we would have to find something about the position function in order to use this nice formula. Note that in section 5.2, we move away from just thinking about velocity, and we start thinking about a function in general. So in general, for a function f of x and its derivative f prime, if we take the integral of the derivative, we find the integral from a to b of f prime, then we use f to plug in our bounds, and we get the total change in position, or the total change in the function. So we can say, like a little analogy here, velocity is to position as the derivative is to the function. And we actually call f of t an antiderivative of f prime. It's going backwards through the derivative process. So this is going to be our result for this section, the fundamental theorem of calculus. So this is going to be the first part of the fundamental theorem of calculus. There's going to be a second part we introduce in chapter 6. So this says, if our derivative, f prime, is continuous on the interval a to b, then, exactly what we said before, the integral of f prime from a to b is equal to f of b minus f of a. So if we are able to find the original function, whose derivative is f prime, then we can easily find the value of the integral. And this allows us to find the values of the integral without having to deal with Riemann sums or limits of Riemann sums or finding exact areas. This is a very, very useful thing. This is how we're going to deal with almost all integrals that we come across. I want to make clear that this result is often stated in a different way, and the difference is just in notation. So sometimes we use f of x as the function inside of the integral. So then the thing on the other side is going to have to be the antiderivative of f of x, and we're going to call that capital F. So here, the derivative of capital F is lowercase f. Some people prefer it this way. I think it adds another notation that's a little bit more confusing, so I'm just going to stick to the f prime and f notation as we had before. But you may see it this way, and really all it is just a small change in notation. So let's see this at work, this fundamental theorem of calculus, and see how it works. So first example, find the integral from 1 to 4 of 2x dx. So here, 2x is f prime. This is our derivative. So what we need to do is we need to find a function, f of x, whose derivative is 2x. This is going backwards through the derivative process. And after some thought, you may find that a function f of x equals x squared does the trick. If you think about x squared, you take the derivative f prime and you get 2x, and that's what we want. So the fundamental theorem of calculus says that this integral from 1 to 4, 2x dx, is going to be equal to x squared, and we're going to use this notation, this vertical bar from 1 to 4. So what does this vertical bar mean? This is an evaluation bar. And it means to plug in 4 and then subtract plugging in 1, exactly what the fundamental theorem of calculus tells us to do. And it's an intermediate step that allows us to kind of organize our information. So what this step tells us to do is to plug in 4 into that function, 4 squared, and then subtract off plugging in 1 into that function. Note that that is f of 4 minus f of 1. That's going to be 16 minus 1, which is 15. And that is the answer to this integral. So let's do it again. Let's have the integral from 0 to pi of cosine of 3t dt. In this case, we are given what the antiderivative is. So we're saying cosine of 3t, this is our derivative, f prime, and we know that the derivative of f here is equal to f prime. So that means that our 1/3 sine of 3t, this is our antiderivative that we're looking for. And you can verify that. If you find the derivative of 1/3 sine of 3t, You can use the chain rule. The derivative of sine is positive cosine. Multiply by 3 on the outside, and you get just cosine of 3t. So that's something that you should verify on your own. So the fundamental theorem of calculus tells us to do this integral. The integral from 0 to pi of cosine of 3t dt is going to be equal to 1/3 sine of 3t evaluated from 0 to pi. So that evaluation bar means that we are going to plug in for t our pi, and then we're going to take that same function and subtract off, plugging in 0. And note that sine of 3 pi here is 0, sine of 0 is 0. This is all just going to be zeroed out, and that is our answer. And what this really means is that the integral of cosine of 3t, which is going to look something like this, so from 0 to pi, looks something like this. The area, the positive area, counterbalances the negative area, and the total area is just 0. So note that when we're doing this problem, and I'm going to try to make this clear in future videos as well, how I'm showing my work. I'm connecting everything with equal signs. I'm not skipping steps. I'm definitely not forgetting to write dt here at the beginning. I'm going to do this intermediate step with the evaluation bar every time. I'm plugging in my values and I'm showing my work. A lot of errors that students have in doing integrals comes down to with the notation and not showing work effectively. In the next video, we're going to do some more practice problems trying to understand this fundamental theorem of calculus and how to use it, and then know that we're going to use this theorem for the rest of the course very heavily.